Swayam Prabha. Digital India. Educated India.
Get started with discussing thermodynamic properties. Set this equal to 0 and then entropy. We have S of T0 P0 plus, no, it was minus, so it is R by P minus dou V by dou T there is a minus R ln P. I think that is the correct expression. You can check it out, there may be a plus R ln P0 minus R ln P, is that okay? Yeah, thanks. So these are the two expressions that we use, and we started drawing the chart. If you plot enthalpy here, it is usually one intensive variable on the y axis, and clearly the isenthalpic lines are simply vertical lines and the isobaric lines are like this. Question is, what about the other lines? You looked at isotherms. If you look at isotherms, write this as T ds plus V dP and ds is Cp by T dt minus partial of V with respect to T dP. If you look at isentropic lines, for S is equal to constant, you get partial of H with respect to P. Remember, partial of H with respect to P is the inverse of the slope on this diagram. And this is clearly equal to T. H with respect to P at constant entropy is something, sorry, V. Okay, then if you want V is equal to constant, you get partial of H with respect to P at constant V. There are several ways of deriving it. This is equal to partial of H with respect to P at constant S. If you treat H as a function of P and S, you get dH is equal to T ds plus V dP. So if you are differentiating this with respect to P, you get dou H by dou P with respect to dou h with respect to dou p at constant s plus this term plus t dou s by dou p at constant v. This first term is of course v, h with respect to p at constant s is v. Doing something wrong. V plus T dou s by dou p, that is correct, and to get ds s with respect to p you have to write s dt and v dp. So s with respect to p would be the second partial of a with respect to t and p, and that is equal to the second partial of a with respect to t and p. So you should get v with respect to t here. This is correct, something, yeah. At constant t. V with respect to p is always negative, and therefore this term is actually greater than dou h by dou p at v. I will rewrite that in terms of measurable quantities. When I have declared measurable quantities, we said the caloric measurements give you Cp, Cv and C sigma. I will discuss this later. The other quantities are P, V and T, or I will put capital T itself, absolute temperature, and then its derivatives. These are usually reported as 1 by V dou V by dou T. This is the expansion coefficient. And 1 by V dou V by dou P, since volume always decreases as pressure increases, minus of it is a positive quantity. So with the minus sign, this is called the constant T is called the isothermal compressibility. And it so happens that the isentropic compressibility or the adiabatic compressibility under reversible conditions, this is adiabatic, sometimes referred to as adiabatic. I should write isentropic. This is of experimental importance because I can show you that, and this is actually directly related to the velocity of sound measurements in a fluid. And velocity of sound are relatively easy to measure compared to most thermodynamic properties. So this is an important property. This is chi sub s. I do not exactly remember what Smith and Van Ness uses. Usually they use alpha for this expansion coefficient, and this is beta or chi. In some books it is chi, in some books. So when I have partial of V with respect to P at constant temperature, so this is actually simply minus V times chi of T. So this is equal to V into 1 plus chi of T, T times chi of T. t times chi of t is dimensionless. Actually it would have been nicer if people had defined that as the coefficient, and you do not have to worry about dimensions, but in practice chi of t is reported in degree k minus 1. So you multiply by t, and so most tables will give you degree k minus 1. So first of all, the isentropic lines, when v is equal to constant, so let me write the slope of these lines. Apart from these measurable quantities, the caloric measurable quantities will include enthalpy changes, phase changes, enthalpy changes during a phase transition. I will come back to that. There are some more measurable quantities, but these are fundamental ones. Let me get back here and say the slope here, you are looking at dou p by dou h at constant volume is simply 1 by v, I am constant s, and dou p by dou h at constant volume is 1 by v into 1 plus t times chi sub t. So this slope on the pH diagram is less than dou p by dou h. So the isentropic lines have a slope that is less than the isochoric lines. So on this graph, I will draw this in anticipation. I am drawing some figures. The graphs usually look like this, all thermodynamic diagrams, some exceptions like carbon dioxide, I will come back to it later. There is usually a liquid region, a liquid plus vapor region, vapor region. Let us say I am looking at the vapor region for now. If I am looking at the vapor region, we have already seen that isotherms would go like this, or we should draw the critical isotherm and then one far away. Okay, this is T is equal to Tc, above this is vapor. Actually technically this portion is called gas, and this portion would be vapor between the gas and below the critical line, but we will not make the distinction as far as property representation is concerned. Gas and vapor, the equations of state are the same, everything is same. But in this region, this is the critical isotherm. If I am looking at this region, I am looking at slope of these curves. First of all, the slope here is always positive, okay, unless the volume gets to be infinity. If you like, I will write greater than or equal to 0, and the slope here is less than this slope, but it is also positive. So it is always a positive slope line. So one line could be like this, the other line which will be of a higher slope. So this is constant S lines, this is constant V lines. So you get these lines, isentropic lines, and you got isothermals, isentropics and isochores, and then you got the isobars which are horizontal and the isenthalpic lines which are vertical. You have essentially all the information you need. So if I am looking at work comparisons, suppose I have a pure fluid, I have an alpha phase and a beta phase. If I write the two laws down, I have TdS for a closed system, TdS minus PdV, these equations are valid for a homogeneous phase. So if I am writing a mix of two phases, U is equal to U alpha plus U beta. Simply the internal energy is sum of the alpha phase internal energy plus the beta phase internal energy. So if I rewrite this, I get du alpha, or I would like to write it actually for G, it is more convenient to write it for G. dG will be minus S dt plus V dP. Right. Similarly for G also, this is equal to dG alpha plus dG beta. I should write here is less than or equal to. So this is also less than or equal to. So this is minus S alpha dt alpha minus S beta dt beta dg is equal to this is less than or equal to. Plus V alpha dP alpha plus V beta dP beta. I should have actually written it for, I am looking at this, I am looking at the closed system, which is the sum of the two phases. Since I am looking at a closed system, I should have started with A. Let me, because basically what I have to do is put constraints on the system and ask when it goes to equilibrium. In the constraint I can put on a closed system which contains two phases is you do not do any work, that means there can't be a volume change, so the total volume should remain a constant. If I want to impose a total volume constraint, I should consider A is a natural function of T and V. I am going to consider an isothermal system with a constraint of V equal to constant, total V. So if I am considering T and P constant, then dG is the natural variable. So let me come back and write this, dA is less than or equal to minus, I can come to the same conclusion here, but it is much nicer to do it with the correct variables. And you have a choice of variables, you may as well choose the natural ones. If you are doing adiabatic isothermal systems, I am sorry, not adiabatic isothermal, adiabatic systems with pressure as a variable, then you have S and P as the natural variables, you choose H. It is, the equations are simply U is a natural function of S and V, H is a natural function of S and P, A is a natural function of T and V, and G is a natural function of T and P. So we will use this as a thumb rule, whenever depending on the variables and depending on the constraints we have to impose on the system, we will choose the independent variables. You can choose any two variables as far as pure systems are concerned. Incidentally, that is purely empirical information. We know from experience that given two variables I can reproduce the state of a pure substance. It is always empirical information at all levels. So if I have this, then I have dA alpha plus dA beta is equal to 0 for equilibrium. With V alpha plus V beta equal to constant. This comes from, you lay the condition that no work is done on the system, it is done on or by. The question itself is asked under those conditions. If you keep on doing work on a system, it is not going to be at equilibrium. So first you stop interfering with it and then you ask when does it reach equilibrium. This is a closed system, but if you look at A for alpha phase alone, this can exchange molecules with the beta phase. So not only is the temperature and the volume of the alpha phase, not only are the temperature and the volume of the alpha phase variable, the extent of the alpha phase is also variable. So I should first write A in an open system of constant composition. A is a function of not just T and V, it is also a function of the number of moles. If I keep the number of moles constant, this is specific Helmholtz energy, it is a function of T and small v, specific volume. but if you write it for the whole system, which is what we are writing here, I should have written this. This implies dA is equal to partial of A with respect to t, which would be minus S, because that partial is taken holding V and N constant. If you hold N constant, you are talking of a system of fixed number of molecules. So this is still minus S dt, there is still a minus P dV. When you differentiate with respect to V, you get minus P plus A with respect to N dN. Now if I write the same thing for G, I get dG is equal to minus S dt plus V dP plus G with respect to N dN. Notice this A with respect to N is holding T and V constant, the G with respect to N is holding T and P constant, and write that out explicitly. TV, and this is T comma P. And by comparing these two, you know G is equal to A plus Ts. So if you A plus PV, so if you differentiate dG plus d of PV, you get minus S dt minus P dV exactly. So by this comparison, you know these two are the same. Partial of A with respect to N at constant T and V is equal to partial of G with respect to N at constant T and P. The variables that you hold constant are different. In fact, this is also equal to partial of U with respect to N holding S and V constant. This is also equal to partial of H with respect to N holding S and P constant. This is because of the redundancy that we introduced. U was the only independent quantity, you introduced H, A and G. U and S were the independent quantities, the others were introduced by combination. This quantity comes up again and again, and for reasons that Gibbs intuited, it was called the chemical potential. I will come back to why it is called the chemical potential. So when I write 3 lines here, it is a definition. So up to here I am right, I need to add a term here. From equation for A, you get minus S alpha dt alpha minus P alpha dV alpha. A is minus S dt minus P dV plus mu dN. So I will have to add here plus mu alpha dN alpha, and here I have to add plus mu beta dN beta. Similarly here also I have to add the same thing. I think I will just put the arrow there. So that term will have to be added to both those equations. I will have to redraw this. I do not know when we are getting the full board. We have one more constraint, because V alpha plus V beta is constant, and because it is a closed system, just like this is constant because no work is done, the system as a whole, two phases together do not exchange mass with the surroundings. We are looking at a closed system. Therefore N alpha plus N beta has to be equal. So in these equations, dV alpha is equal to minus dV beta, dN alpha is equal to minus dN beta. So I have dV alpha is equal to minus dV beta, dN alpha is equal to minus dN beta. So I have dA is equal to, for the whole system, is minus S alpha dt alpha minus S beta dt beta then minus P alpha minus P beta into dV alpha minus mu alpha minus mu beta, this is plus dN alpha. This should be equal to 0, this is the criteria of equilibrium. The two laws combined will tell you dA is less than or equal to, on the right hand side, this is the criterion, this is equal to 0 at constant T and P, at T and V, at constant T, that is all. For a closed system it is at constant temperature, because I have already held the volume constant, I put V alpha plus V beta equal to. So at constant temperature I know A has to be a minimum, therefore dA has to be equal to 0. Now out of these I have constant T, which means then I have to specify further conditions. When I say equilibrium, I ask for three kinds of equilibrium. I ask for thermal equilibrium, which means T alpha is equal to T beta, is equal to T, say, we just label it as T. The two temperatures have to be equal. I ask for mechanical equilibrium, which means P alpha is equal to P beta is equal to P, some given pressure P. So first I have thermal equilibrium, which means temperatures have to be equal. I know if temperatures are not equal, heat will be transferred from one to the other, that is my 0th law. So as long as changes occur I cannot have equilibrium. So this term is 0 because of thermal equilibrium, T is equal to constant and thermal equilibrium. Thermal equilibrium demands that the two phases have the same temperature, and I have put T is equal to constant. Mechanical equilibrium demands that P alpha is equal to P beta, therefore this term is 0. I am not setting P equal to constant, all I am saying is the two pressures have to be equal. The criterion of equilibrium says dA should be 0 at constant temperature for a closed system. I am saying if the pressures are unequal, then one phase will do work on the other phase, it will expand till the pressures are equal, and so I have to have P alpha equal to P beta, whatever the value of P. If this has to happen, this implies this criterion of equilibrium, we will call this equation 1. Equation 1 then implies mu alpha should be equal to mu beta. So A is the natural variable to consider because I can build in the work function correctly. I could have done it with the G equation as well. Notice that the law really says dA is less than or equal to 0, and what you get is dA at constant temperature and conditions of mechanical equilibrium is equal to mu alpha minus mu beta from dN. This is thermodynamics, the two laws at constant temperature. Constant temperature, no work. This is calculus. From calculus alone you won't draw any conclusions in thermodynamics, you have to always use the law at some point. Calculus is just going to give you equalities, so you got this result, and from thermodynamics this should be less than or equal to 0, and I am saying at equilibrium it has to be equal to 0 because it would have reached a minimum, and if mu alpha is not equal to mu beta, let us say example mu alpha is greater than mu beta, then dn alpha can be of any sign. If I choose dn alpha to be positive, I increase the number of moles in the alpha phase. If dn alpha is negative, I decrease the number of moles in the alpha phase. In this I have a choice, and by definition as a thermodynamist I will be as perverse as possible, and you still have to show that the law is valid. So if you give mu alpha is greater than mu beta, this is positive, I will simply choose dn alpha to be positive, and so the energy will increase. I mean I will choose dn alpha to be negative, so I can decrease the free energy further. If I can decrease the free energy further, I am not already in a state of equilibrium. If I am currently in a state of equilibrium, it should be impossible for anybody to reduce the free energy of the system. Now let us say I am now in a state of equilibrium, then there must be no possible way for me to decrease the free energy. If this was greater than this, I would simply take away moles from alpha phase and decrease the free energy. I should not be able to do that. Conversely, if mu alpha was less than mu beta, I will choose dn alpha to be positive, I will add moles to the alpha phase and decrease the free energy again, and thermodynamics says you can never do it if you are already at equilibrium. Therefore the conclusion, that is then dn alpha less than 0 would lead to decrease in A. If mu alpha is less than mu beta, dn alpha greater than 0 would lead to decrease in A. Neither is possible if you are already at equilibrium. Neither is acceptable if the system is already at equilibrium. So this implies mu alpha is equal to mu beta. And Gibbs called it the chemical potential because if T alpha is greater than T beta, then you have a temperature gradient and heat flows in the direction of the decreasing thermal gradient. Similarly, if mu alpha is greater than mu beta, then heat moles would be transferred in the direction of decreasing mu alpha, so that the free energy decreases. So he called this the chemical potential. It's probably the most important variable in chemical thermodynamics. I don't know if you have read, this is your reductio ad absurdum proof, right. When you sort of assume, let us assume mu alpha is greater than mu beta, then by transferring moles away from the alpha phase I can decrease the free energy, which is absurd because I am already at equilibrium. So you assume first of all that you cannot decrease the free energy, and then you show that if this is true then you can decrease the free energy, then you could not have been at equilibrium, or this is not true. So what we have is we proved that mu alpha is equal to mu beta. Then let me also integrate the basic equations, and again this is very typical of thermodynamics. In particular I will take this equation, this is the most easy convenient equation for most purposes. You can do this with any of the equations that you have in thermodynamics. So I am writing the basic equation for an open system. Basic equation for open systems. Now I want to integrate this. I am going to do something. This is system at t is equal to 0, t time equal to 0, this is system at time t. Now at time what I am going to do is I am going to connect it to a reservoir. This contains fluid at some temperature and pressure P. In the reservoir I have the same fluid at the same temperature and same pressure. My process is the following, the whole thing is a thought experiment. I simply take this box, I add more fluid to the reservoir and make sure its volume changes so that the T and P remain the same. The only difference between these two states is I have n moles here, I have k times n moles here. I keep the extensive variables the same so that the specific state of the system remains the same. If I take 1 mole of the substance here, 1 mole of the substance here, the state is the same because T and P are the same. The first argument is if T and P are the same in this process. For this process, if I take a calculation of dg, this is 0, this is 0. Mu by definition is partial of g with respect to n at constant T and P. I claim this is an intensive variable because it is the property, it is the partial molal property. So, I am really calculating g per mole of addition. G is extensive, n is extensive. I am asserting that partial of g with respect to n is an intensive variable. If it is an intensive variable, it can be a function only of T and P. You might say this is in a fundamental way an assumption in classical thermodynamics. But let me come back. Right now, if mu is an intensive variable, it must remain the same here as here. So, for this process, G final minus G initial is simply equal to mu times n final minus n initial. This is k minus 1 times G initial, which is simply G, mu times k minus 1 times n. Ni and this is the same as G. Use the notation in the initial state. The initial state has n moles and its free energy, Gibbs free energy is G, and k need not be 1, therefore I can strike this off. This is valid for all k. So, G is simply equal to n times mu. So, although we introduced a variable mu as the partial of G with respect to n, in the case of constant composition systems or in the case of pure substances that we are now dealing with, mu simply happens to be small g. So, this is G by n, which is by definition small g, is also equal to mu. So, the specific Gibbs free energy is exactly the chemical potential. You can see the relationship with other variables because you have introduced this redundancy H is G plus Ts. So, if you are doing partial of H with respect to n, you will get partial of G with respect to n, which is mu, plus T partial of S with respect to n. And you can do the same thing with A is G plus PV. So, H with respect to n is mu plus a quantity. The only partial that is exactly equal to the specific property is the Gibbs free energy. The specific Gibbs free energy is the chemical potential. Okay, having said that, now let me go back and look at our equations for equilibrium. So, the equilibrium equation said mu alpha is equal to mu beta if you have two phases. You can derive the Clausius-Clapeyron equation from this because d mu alpha is equal to dg alpha, you have done that before. But this gives you H alpha minus T S alpha is equal to H beta minus T S beta. H alpha minus H beta, let us say, is delta H is equal to T delta S. And delta H is a measurable quantity. You know that there is a latent heat you can measure, you can do this in experiment. So there is a positive difference in enthalpy between two phases. So we have done this part. This is your critical isotherm. In this region we have seen two sets of curves. I think this is constant S, this is constant V. Right. Now if you come to, if you go below the critical region, the lines here are vertical as we have pointed out because it is ideal gas. At low pressures you can exactly calculate this ideal gas behavior as vertical lines. So at constant temperature we are saying thermal equilibrium means you are looking at an isotherm, mechanical equilibrium means you are looking at the pressures being the same, you are saying the enthalpy of one phase is greater than the enthalpy of the other phase. So there will be a shift here in the enthalpy. This quantity is your delta H for phase change. This in case can be the alpha phase, this can be the beta phase. The enthalpy is larger by convention for vapor. So you get vapor here and you get liquid here. This is liquid plus vapor in between. This delta H is a function of temperature. If you go to lower temperatures you find the width, experimentally you can show the width actually increases. So delta H will increase as you go down in temperature. We can do the calculation for that in a minute. So I have done this portion. The isotherms here you can calculate the isotherm slopes. You again have dH is equal to Cp dt plus V minus T dou V by dou T to dP. So at isotherms this is, along isotherms this is 0. So partial of P with respect to H is simply 1 by V into 1 minus alpha. This is the expansion coefficient. 1 by V dou V by dou T is a measurable quantity minus alpha T, sorry. For an ideal gas alpha T becomes 1 and therefore you get infinite slope in those lines. Here also the slope is reasonably steep because 1 minus alpha T becomes somewhat small. Here actually 1 minus alpha T is non-zero but V itself is small in the liquid region. So you got high pressures you get steep slopes. So the isotherms are always somewhat steep. So what happens is I have got these isotherms, I have got the difference in the enthalpy. So the isotherm will have to come like this, there will be a difference in the enthalpy, then there is the other half. So this side is the vapor region, this side is the liquid region. What we can do is actually calculate this whole thing. I would like you to compute it for a van der Waals fluid, because in order to give you information I have to give you Cp, and so I have to give you Cp, the specific heat, and PVT information. PVT information, for example, you can take the van der Waals equation. He said P plus A by V square into V minus B is equal to RT. The van der Waals fluid is of great importance for two reasons. First, it was the first historical equation of state that took into account attractive forces, and secondly it has no qualitative contradictions. You have to show that the quadratic form is positive. If you show that, you can show what are called stability criteria. You can show V always has to decrease as pressure increases, things like this which you take for granted, or you take for granted that some of these coefficients are positive. They all come from this requirement of stability. Stability is not usually discussed in undergraduate classes, so I will not discuss it further. It is only simple calculus, it is putting down criteria of calculus on the second derivatives in the equations in order to show that A is actually a minimum and not a maximum at equilibrium. So this equation has no qualitative contradictions, it satisfies all the thermodynamic stability criteria qualitatively. It does not agree with experiment, but qualitatively it is one of the few equations of state that is completely free of faults, therefore it is of importance.